This question here is the height of water in part was measured over time. The average height was found to be 1.6 meters, and the height was measured in HT using the model of the function HT equals 1.6 plus 1.5 cos pi over 6t, where t represents the number of hours since the last recorded high tide, and pi over 6t is expressed in radians. Find the period and range of HT. Now, my advice to you guys would be to enter this into the function of your calculator and get a quick idea of what's going on. I'm going to quickly use the GeoGebra package. My hope is here that I can give you a quick look at what this diagram looks like and what exactly the question's trying to get at. Okay, so what we're going to do is just going to draw this graph. Okay, so I put it as y or f of x equals 1.6 plus sine plus 1.5 cos pi over 6. So pi being, let me see, I think you can write pi in the pi divided by pi times x actually. Pi times x divided by 6. Okay. Press equals here. Now it will show you what exactly is going on. Okay, so we can see here that at t equals 0 we have a high tide. Okay, and when t equals 0 it's of a certain height. Then we go all the way down to low tide where t equals 6, and then we go all the way back up to another high tide which is t equals 12. Okay, so you can see how the function works. Okay, now the deal is with cost functions, find the period and range of h of t. Okay, so when you're doing these questions, all right, what you have to figure out is how long does it take for this to be going. So we'll just take a quick snapshot of this just so we can use it. The same one. And here we go. Now, what exactly is going on here? So this is the starting off tide and it's on its way down. Right? Then it goes all the way back up here and it's on its way down again. Remember, functions repeat every 360 degrees. Okay? So the functions repeat every 360 degrees. 360 degrees is equivalent to 2 pi. So when does the function reach 2 pi is what you should be asking yourself. Okay? So when you go back, you can just see it here. When does this function part here, is the important part, when does this reach 2 pi? It reaches 2 pi when pi over 6t equals 2 pi. And what you can do there is cross the pi's off both sides, multiply t by 2 by 6, and you get t equals 12. You're going to have a period of 12 hours. Okay? Another way to get the period is the period. There's a formula for that where period equals 2 pi, and it's always divided by the coefficient that comes in front of the variable in the angle. So it can be cos, sine, whatever, but it's the number that comes in front of the variable. T is the variable, so it can be 2 pi over pi over 6, and that once again will get you an answer of 12 seconds. Okay, now the next question is, what do you do to find the range? Now the range is basically high tide minus low tide. Okay, and if you look at the diagram here, high tide versus low tide is like this. High tide is at the top. You can see it here at 3.1 meters, and low tide is down here. Now, how would I find out where these functions are? How do I know that that's low tide and that's high tide, all right? Well, the cos function has a maximum. The maximum of that function is usually when t equals 0, or is usually at t equals 0 or t equals 2 pi. Okay, so the angle itself, not t, it's when the angle equals 0. So once again, we'll just highlight this. The maximums will occur when this part here either equals 0 or 2 pi. Okay, but when are the minimums? The minimums always occur halfway between the two maximums. So the minimum will occur when this angle, this full angle here, equals pi. Halfway in between 0 and 2 pi is pi. So this one here is when the angle equals 2 pi. This one here is when the angle equals 0. And halfway in between would be where the angle, the whole yellow thing, equals pi. That's why you have pi over 6, t equals pi, and you figure out that t equals 6. It occurs after 6 seconds. Okay. Now, what you do is you use your calculator function. You can find out when the maximum and minimums are. Okay. You do the table function, or you could work it out manually. To work it out manually, all you have to do is h of t equals 1.6 plus 1.5 cos pi over 6. You can use t equals 0 because that will give you the height here. So we can just do pi over 6 times 0. Put that into your calculator, you're going to get 3.1. Like this, you get the same answer if you use t equals 2 pi, would give you the same answer. Now, in this one here, what we have is we have a t value of 6. So it's going to be 1.6 plus 1.5 cos pi over 6 times pi. And what this one's going to give me is a log of 0.1. So the range in question is 0.1 to 3.1. Is that okay with you guys? Now, moving on to the next question. Whatever that might be, I can probably just get rid of this for a minute. Cut it. Find the maximum height of the water in the pot. Now, let me see. Oh, sorry. I actually have to go back on this. My fault. Not having my table function has actually messed me up here a little bit. I'm just going to not having a calculator on screen. I'm just going to put it into my calculator if you don't mind, and I'll show you one again. I forgot all about the median height is found to be 1.6. See this median height, the average height was found to be 1.6. So that average height would be somewhere in here. That's your average height right there. Okay, that's like almost like your baseline. Okay. Turns out everything's a-okay anyway, so everything I told you already is grand. All right. So what we're looking at here, just going to get rid of this again for 1 second, and from what we learned earlier is that all this here was the height. So the height is actually 3.1. The maximum height of water in the first 3.1. Already found that using this here. So you can just simply repeat that procedure, and you get a maximum height is 3.1 meters. We already found that from the range. Okay. What's the next thing it wants from me? It wants me to find the rate at which the height of the water is changing when t equals 2, correct 2 decimal places. When you see the word find the rate, that's a differentiation question. And I want it when t equals 2. So let me show you what to expect here, right? So when t equals 2, what we're looking at is it's on a downward trajectory. See why t equals 2 here? That's t equals 2. Look at it, it's a negative slope. It's on its way down. So when we differentiate this and insert t equals 2, what we're expecting to happen is we're expecting this to be a negative answer. Okay? And let's see if this is the case. Okay? So find the rate at which the water is changed when t equals 2, correct to 2 decimal places. Explain your answer in the context of the question, right? So what we're going to do is differentiate. So h of t, which is the original function, equals 1.6 cos 1.6 plus cos plus 1.5 cos, excuse me, 1.5 cos pi over 6t. Okay. Now, when we differentiate this, what happens is the normal numbers turn to 0, so that's a 0. Now, the angle always remains the same, and cos will turn into minus sine, so it's going to be minus sine pi over 6t. That's what I'm differentiating. Now, there's hidden parts involved here. The 1.5 goes straight down as well, so the 1.5 is still there. And we also have to differentiate the angle, okay? So when we differentiate the angle, what we're going to get is just pi over 6. Okay? So this equals pi over 6. So what we're going to get is 0. So it's 1.5 multiplied by pi over 6, which is going to be minus 1.5 pi over 6. All right? And then what we're going to have here is we're also going to have sine pi over 6 times t. Now please remember that the t is going to change. The t is now going to be worth 2. So you take that out and you put in t equals 2. Use your calculator, make sure it's in radian mode, and put all of this into your calculator. When you put all that into your calculator, what you should get is minus 0.68017. And what this means, as predicted, it was a negative answer. And what this means is that your tide is currently reducing by minus 0.68 meters per hour. So at 2 a.m., because it's t equals 2, right, and t equals 0, where does it say t equals 0? T is never recorded, so period times x apart. So it doesn't say anything about t equals 0 being midnight, does it? The high water. So the way I would say this is that after 2 hours, 2 hours after the last high tide, the the rate of the tide is lowering itself. The level of the tide is becoming lower at a rate of 0.68 meters per hour. Please remember, t is in hours, and your height is measured in meters. So the rate would be meters per hour. Okay. What's the next question? Sketch a graph of HT between midnight and the following midnight. Well, lucky for me, I've already done this. Now, it says it starts at midnight, so that means that 2 a.m. slot, which we were looking at here a second ago, this 2 a.m. slot must have been the 2. This must be 2 a.m., so it's 2 a.m. in the morning. Now, I'm very much going to just use what I have here as the sketch. So maximize my time. All right, so sketch this graph, no bother. I'll just make it fit. So paste it here. So it's 12 hours between one high tide and the next high tide, all right? So that's not going to really fit too good here, because what we need to have, I'm going to need, it says 1 midnight to the following midnight. I'm going to need t equals 24. So I'm going to have to go back here. I'm going to narrow this graph up. So this is the sort of graph we're expecting from this. Don't mind. Put this. Okay, just bring this in. And there is from, and then we can drag this a bit further upwards, like so. And then maybe even go a bit taller. There you go. Okay, so the graph we're looking at is something like this. Starts off at midnight, 6 a.m., 12 p.m., 6 p.m., 12 p.m. So the graph you guys should draw would be something like this. So your graph should look something like that. You can just draw it into the table function. And there it is there. that should be our graph there. See the way we can match up to the 3. Then I'll just drag it down all the way to 0. 24, so the 24 will line up with the midnight part. And your graph should look something like this. Vary it all up and down, like so. Okay, now what's the next question after that once we draw that graph? From your sketch, the difference in water height between high and low tide. So between high and low tide, so from your sketch to find the difference in the water height between high and low tide. Well, what you might do there is you're just going to go to here, and you're going to draw a line going straight across from the low tide. You might estimate that, I don't know, at 0.1 or whatever you're going to, everybody's answer is going to be totally different. I'll estimate that at 0.1, and then go to high tide, and then I'll estimate that at 3.1, 3.2-ish. Okay, and once again, your answer for this question here will be, excuse me, will be 3.1, take away 0.1, and that will get you your 3 meters. A fully loaded barge enters the port. It unloads its cargo and departs sometime later. The fully loaded barge requires a minimum water level of 2 meters. When the barge is unloaded, it only requires 1.5 meters. Use your graph to estimate the maximum time the barge can spend in port. So when it comes in, it has to be 2 meters high. Okay. So what we can do is we can go back here. Okay. And we can scroll down. Now it needs to be 2 meters. Okay. So what we do is 2 meters here. So that's when it enters the port. And we could technically, now when does it give me a time for when it enters the port? Okay, so 1.5, 2, 1.5. So it comes in at 2. Let's say it comes in the morning. That's 2 meters right there. So we go straight down. And say that's somewhere halfway between 2 and 3. Let's call that 230. Okay. And then let's look for 1.5 meters. Now we're talking about we won't be able to leave port straight away because it's stranded because it hasn't unloaded yet. So then we're going to wait to the neighboring 1.5, which is here. So we're going to wait to the neighboring 1.5. So this 1.5, it's still full. It hasn't unloaded yet. So you got to wait your turn. Then you come down here. And then you're going to get like roughly 9, let's say 8 or 9 in the morning, right? So we're talking about 2:30 to 9-ish. So h equals 2h is 1.5, and then take away your maximum from your minimum. I'd say that does something around 9 o'clock. So what I'm getting is 6.5 hours, okay? And maybe 2:30, maybe that's 3. 2:30 might be a bit forgiving on that. Maybe it's more like 6 hours, okay? Now, I could check the results out there. If I wanted to make it really accurate, I could just put in a p equals. I could find out the angle, but best to do it on graph for this one, lads. Okay, let's do it on the graph, and I can show you a more complicated way of doing that tomorrow. Okay, so that's basically uh, 9 o'clock minus 3 o'clock gives me roughly 6 hours. Okay. Now moving on. What we have here is a table that needs completing. Okay. Now to do this, what we're going to do is we're just going to put it into your table function. And what you're all going to get is 0, 5, 8, 9, 8, 5, 0. Fine, use the trapezoidal rule, okay? So the trapezoidal rule, I'll try to a quick diagram of this. Give me one moment. Okay, so we put this into our table function. We get 3, 0, 4, 5, 5, 8, 6, 9, 7, 8, 8, 5, 9, 0. Now I'm just going to show you a quick diagram of this just for a bit of perspective. This is what it looks like. It's an N-shaped graph. No hassle there. Okay. Now what we're going to do is we're just going to examine the heights, which we already know. So this is what it actually looks like on the graph. That last one should be, sorry, excuse me, a bit taller. Try again. Okay. Now look for this. Then all the way to the top here, like so. And then next one. Start really far down. There you go. Next one after that. There you go. So there's all our heights there, okay? So height of 5, height of 8, height of 9, height of another 8, height of 5. Please remember the first and the last are both zeros. Okay? And the width is going to be equal to 1. Okay, so the width here is going to be equal to 1. So when we're doing the graph, it's h over 2 first plus last plus 2 times the remaining. Okay? And when you do this, the h value is 1. So it's going to be 1 over 2. The first is 0. The last is 0. 2 times the remaining is your 5 plus your 8 plus your 9 plus your 8 plus your 5. Goes down. Put it on the calculator, you're going to get 35 square units. Okay, because you don't know if it's meters or not, or centimeters, so you have to say square units. Now, use your answers above to find the percentage error in your approximation of the area correct to one decimal place. Well, what we're going to do is we're going to calculate the area of this from x equals 3 to x equals 9 using integration. So what we can do is, maybe there's another part, so I have to find this here. And this part here will actually give me the size of the area. So 93 f of x, which is minus x squared plus 12x minus 27 dx. Integrate that. We're going to get minus x cubed over 3 plus x squared minus 27x from 9 to 3, which is equivalent of me saying minus 9 cubed over 3 plus 9 squared minus 27 times 9, close bracket. And then we got take away from that minus bracket 3 cubed over 3 plus 3 squared minus 27 times 3. Follow that to the calculator, and we're going to get 36 square units. Now, percentage error is basically your error of your true value multiplied by 100%. Our error is 1, our true value is 36. We multiply this by 100, and what we're going to get is 2.8%. Okay. Now, moving on to the next question. Okay, so question after that is, an oil spill occurs offshore in an area of calm water with no currents. The oil spill in a rate, the word rate again usually refers to differentiation. The oil floats on top of the water. Completely below to show the volume of oil on the water after each of the first keyword there is volume of oil of each of the after first 6 minutes of the oil spill. Okay, it's spilling at a rate of 4, so it's going to be 4, 8, 28. And look, I'll just go all the way to 624 because if it's linear, it's all the points are the same. No, that's not it. Go again. There you go. Now we can put all the points in afterwards. Easy. Okay, so the volume has gone up by 4 per second. Write equation phi of t for the volume of oil on the water after t minutes. Well, after every minute, there's an extra 4 added. So I would surely say that phi t ends up to be the amount per minute. So how many is it? It's 4 by 10 to the 6 centimeters. So it's going to be 4 multiplied by 10 to the 6. And then just simply multiply that by time. Because the amount of time, if I multiply time equals 3, t equals 3, that'll be 12 by 10 to the 6. And that's measured in 10 to the 6. So that'll be 12 by 10 to the 6. Okay. B. The spill forms an oil slick 1 millimeter thick. A 1 millimeter thick is 0.1 centimeters. Write an equation for the volume of the oil slick in centimeters cubed when the radius is r. Okay, so essentially what we have here, guys, is if you imagine the surface of the water. Okay, and it's a circular oil slick, so it's a circular oil slick like so. But what it does is it has a small height, and its height is 0.1 of a centimeter. Okay, and its radius is r. It's essentially making a cylinder here. It's a cylinder, okay? So it's pi r squared h. So pi times r squared minus 0.1. The volume of this slick is 0.1 pi r squared. Find the rate in centimeters per minute at which the radius of the oil slick is increasing when the radius is 50 meters. And once again, 50 meters ain't compatible with what we've been doing here. Okay, we want 50 meters to be 5,000 centimeters. And it's asked me for rate. So rate is dr dt. Okay, so the rate is dr dt. Now, dr dt is, we have to find out what dr dt is. But remember the chain rule, we've covered this already in our summer test. It's going to be, we have to think of 2 other things. I can do the v dt, but then I need dr dt, okay? So dr dt. I can also do dv dr. You can find out what the VDR is. If I turn the VDR upside down, I get the VDT by dr dv, and the dv's cancel to make dr dt. So here's what we're going to do. You know that v is 0.1 pi r squared. Differentiate that, find the VDR, which is going to be 2 times 0.1, which is going to be 0.2 pi r. Turn that upside down to get dr dv. Turn it upside down, so dr dv ends up to be 1 over 0.2 pi r. 1 over 0.2 pi r. Okay. Now we know the VDT is the rate at which the volume is increasing with time, and we know that to be 4 by 10 to the 6. Okay. So 4 by 10 to the 6. So what we're going to have is 4 by 10 to the 6 multiplied by 1 divided by 0.2 pi r. Remember the r value is going to be replaced with 5,000. And what that's going to get me is dRdt, and dRdt is going to be 1,273.3 centimeters per minute. Okay, next one. Show that the area of the water covered by the oil slick is increasing at a constant rate of 4 by 10 to the 7 centimeters per minute. Area of water, rate of the area of water. So that's the ADT we're looking at there, I believe. And the ADT, we know that A equals pi r squared. So we know what the ADR will be. It says the word circular. So it's going to be 2 pi r. So that's the ADR. And then we could deal with dr dt. Okay. So the ADR is 2 pi r. Okay. The RDT we had on the last part before we calculate it all out. The RDT was all this here, this complete part here. So if I get rid of one, and to my last question, there's my DRDT there. Now we aren't told the radius is 5,000 this time. We're going to change that back into R. Okay, and then we choose this part here, and this part here, and this part here. We just copy it, bring it over here sides. Now this is for DRDT. That's the RDT there. Now we can see that a lot cancels. Okay, so what we have is the R's will cancel, the pi's will cancel. 2 divided by 0.2 is actually 10. So 10 multiplied by 4 to the power of 10 is 4 by 10 to the power of 7. That was reasonably okay. The nearest land is 1 kilometer away from the point at which the oil spill began. Find out how long it will take for the oil slick to reach land. Give your answer correct to the nearest hour. Well, what you got to remember is let's put this point here as the start of the oil slick, and let's put this as land. Okay. What's happening is it's accelerating now as a circle. So the oil slick is expanding, and then it hits land. It hits land when the radius is 1,000 meters. Okay? So the radius is 1,000 meters. Okay? Now, how long does it take for the area to get this big? The area has to be this size. The area is going to be pi r squared. The area therefore has to be pi times 1,000 squared. And pi times 1,000 squared oh, sorry, this is 1,000 kilometers, right? 1,000 kilometers is 1,000 meters. So I got to remember, I actually measuring all this in centimeters. So you got to multiply this by another 100 again. So 1,000,000. That's actually 10 to the power of 5. So what you want to do is, that's in meters. I actually need it in centimeters. So that's going to be 10 to the power of 5. 10 to the power of 5 by 10 to the power of 2. Actually, pi times 10 to the power of 10. Okay? Now, how long does it take for that to happen? Well, we're told in the last question that the area is increasing at this amount here. Every minute it increases by 4 by 10 to the power of 7. Okay. Imagine this. Imagine I needed an area of 50, and I start off at 0, and it goes up 2. The area increases 2 meters squared, let's say, per minute. 50 divided by 2 will tell me that will happen in 25 minutes. Okay. And this is the same concept here. We start off at 0. We're aiming for this like big number here. We want this to happen. This is how much area we want. But this area only happens at a rate of 4 by 10 to the power 7 minutes. So the yellow number divided by the rate, and what you roughly get is a t value. Remember, this is in minutes of 785.398. And then convert that into hours, and t will get you 13 hours. Okay.